Consider the rock in your hand, a paragon of stillness. It rests, heavy and inert, a symbol of permanence. Or perhaps gaze into a tranquil cup of tea, its surface a placid mirror. We perceive these things as static, as anchors in a fleeting world. But this perception, this comforting illusion of stability, is perhaps the most profound deception our senses have ever crafted. For if we could attune our eyes to the true nature of reality, we would discover that the universe permits no such thing as absolute rest. Nothing, from the smallest conceivable constituent of matter to the grandest supercluster of galaxies, ever truly stands still. Existence is a symphony of ceaseless motion, an intricate, unending dance choreographed by the fundamental laws of physics. To understand this universal dynamism is to embark on a journey, a voyage that will take us from the frenetic heart of the atom to the unfathomable, expanding frontiers of the cosmos itself. Our journey begins not by looking out, but by looking in. Let us descend into the seemingly placid world of that teacup. What appears as a serene pool is, in reality, a maelstrom of activity. The water molecules, each a tiny trio of atoms, are in a state of wild, unrelenting commotion. They vibrate, rotate, and collide with unimaginable frequency, billions of times every second, driven by the thermal energy they possess. This is the hidden world revealed by the phenomenon of Brownian motion. In 1827, the botanist Robert Brown, peering through his microscope, observed pollen grains suspended in water. He expected them to be stationary, but instead they jittered and danced. They moved erratically, with no apparent cause. For decades, this was a baffling curiosity, a ghost in the machine of classical physics. It was not until 1905, in his miracle year, that a young Albert Einstein provided the definitive explanation. He theorized that the visible pollen grains were being jostled, pummeled from all sides by the invisible, hyperactive water molecules. Imagine a colossal beach ball being pushed and shoved by a crowd of thousands, each person pushing in a random direction. The ball would tremble and wander, its path a testament to the chaotic energy of the unseen multitude. This is the reality within every drop of water, every lungful of air, every solid object we perceive as motionless. It is a perpetual, microscopic storm, a fundamental kinetic reality that underpins the very concept of temperature. The warmer an object is, the more violent the internal pandemonium. Only at the theoretical and ultimately unattainable point of absolute zero would this molecular agitation finally cease. But our universe, even in its coldest voids, is never truly that cold. The background hum of creation, the faint afterglow of the Big Bang, ensures that a baseline of energy always remains, keeping this microscopic dance alive everywhere, always. But even this frenetic ballet of molecules is not the bottom floor of reality. We must plunge deeper still, into the atom itself. For generations, we envisioned the atom as a miniature solar system, a dense nucleus of protons and neutrons with electrons orbiting like dutiful planets. This is a clean, orderly, and deeply misleading picture. The quantum revolution of the early 20th century shattered this classical model. The electron is not a tiny sphere following a predictable path. According to the principles of quantum mechanics, its existence is far more ethereal. The Heisenberg uncertainty principle, one of the cornerstones of this new physics, dictates a fundamental trade-off in the universe. It states that we can never simultaneously know with perfect accuracy both the position and the momentum of a particle like an electron. The more precisely we pinpoint its location, the less we know about its velocity, and vice versa. This isn't a limitation of our instruments. It is an intrinsic property of nature. The electron, therefore, cannot be a static point. To be perfectly still, its momentum would have to be precisely zero, which would mean its position would be infinitely uncertain. It would, in essence, be everywhere at once. Instead, the electron exists as a probability cloud, a haze of potential locations, surrounding the atomic nucleus. It is a smear of existence, a ghost that is constantly in a state of flux, its presence a shimmering probabilistic dance. It is never at rest. Its very identity is woven from the fabric of motion. To halt an electron would be to violate the fundamental grammar of reality, and the quantum weirdness does not stop there. If we could somehow magnify a patch of what we call empty space, zooming down past the scale of atoms and their constituents, we would find that it is not empty at all. The vacuum of spacetime is a seething, effervescent cauldron of activity. It is known as the quantum foam. Here, for fleeting, impossibly brief moments, pairs of virtual particles, an electron and its antimatter twin, a positron, or a quark and an antiquark spontaneously erupt into existence. They borrow a sliver of energy from the universe itself, permitted by a time-sensitive loophole in the laws of conservation. They exist for an instant, shorter than a trillionth of a second, before annihilating each other, repaying their energy debt and disappearing. This is happening everywhere, at every moment. The void itself is alive with a ceaseless churn of creation and destruction. Absolute nothingness, a state of perfect stasis, is a physical impossibility. The universe, even in its most vacant corners, refuses to be still. It is a restless ocean of potential, constantly bubbling with transient life. The very fabric of spacetime is a dynamic, energetic entity, a far cry from the passive, empty stage envisioned by earlier physics. The stillness we crave is a fiction. The universe is fundamentally, irreducibly, and beautifully restless. Now, let us pull our perspective back, rising from the subatomic chaos. We return to ourselves, standing on the surface of the earth. We feel the ground solid beneath our feet, the epitome of stability. Yet this sensation is a profound illusion, born of our shared frame of reference. We are all passengers on a colossal spacecraft, and its movements are so smooth, so vast, that we do not perceive them. First, there is the rotation of our planet. At the equator, the surface of the Earth is spinning at a dizzying speed, moving at over 1,600 kilometers per hour, or about 460 meters per second. Even as you sit seemingly at rest, you are hurtling through space faster than a rifle bullet. This relentless spin gives us our cycle of day and night, a daily testament to a motion we cannot directly feel. This was a truth for which figures like Galileo Galilei risked everything. The prevailing view, inherited from Ptolemy and sanctified by the Church, was that Earth was the unmoving center of all creation. To suggest otherwise was heresy. But the evidence of the heavens, of the moons of Jupiter, and the phases of Venus was undeniable. The Earth was not static, it was in motion. And this planetary pirouette is merely the beginning of our cosmic journey. As it spins, our world is also careening through space in its annual orbit, around the Sunday. To maintain this orbit against the Sun's immense gravitational pull, the Earth must travel at an astonishing velocity of approximately 30 kilometers per second. That's over 100,000 kilometers per hour. Every minute, we traverse a distance of nearly 1,800 kilometers along our orbital path. Think of it this way. During the time it takes to brew a cup of coffee, you have traveled a distance greater than the width of a continent. All of humanity, our history, our triumphs and tragedies, are being carried through the void on a rock moving at this incredible pace. We are all cosmic voyagers, locked in a gravitational dance with our star. The complex interplay of gravity and inertia, first mathematically described by Isaac Newton, dictates this perpetual transit. An object in motion stays in motion unless acted upon by an external force. In the near vacuum of space, there is virtually no friction to slow the Earth down, and so it falls endlessly around the Sun, its forward momentum perfectly balanced with the Sun's gravitational embrace, creating the stable, life-giving orbit we depend upon. Stillness is not an option. To stop moving would be to cease falling sideways, and instead plummet directly into the fiery heart of our star. But even our magnificent Sun, the anchor of our solar system, is not a fixed point in the cosmos. It too is a traveler on a far grander journey. Our entire solar system, a family of planets, moons, asteroids, and comets, is embedded within one of the spiral arms of a vast stellar island we call the Milky Way galaxy, and this entire celestial structure is in motion. The Sun, dragging the Earth and all its siblings along with it, is orbiting the supermassive black hole at the galactic center. This is a voyage of truly mind-boggling scale. Our speed on this galactic circuit is a staggering 220 kilometers per second. That's nearly 800,000 kilometers per hour. Even at this extraordinary velocity, a single orbit around the galaxy, a galactic year, takes our solar system roughly 230 million Earth years to complete. The last time our planet was in this same region of the Milky Way, dinosaurs were just beginning to roam its surface. The entire history of the human species has unfolded during a tiny fraction of this single, sweeping journey around our galaxy. When astronomers in the 20th century, like Vera Rubin, began to meticulously measure the rotational speeds of galaxies, they encountered a profound mystery. The stars on the outer edges were moving far too quickly. According to our understanding of gravity and the visible matter in the galaxy, these outlying stars should have been flung off into intergalactic space, like water from a spinning wheel. The fact that they were not implied there was a tremendous amount of unseen mass, a gravitational glue holding the galaxy together. This was the first compelling evidence for what we now call dark matter. This mysterious, invisible substance, which does not emit or interact with light, is thought to make up about 85% of the matter in the universe. Our galaxy's majestic, rapid rotation is a direct consequence of this unseen halo, another layer of cosmic activity driven by a substance we cannot even perceive. The Milky Way's very structure is a dynamic testament to this invisible influence. The story of our motion, however, does not end at the galactic border. Even our entire galaxy, this swirling metropolis of 200 billion stars, is itself hurtling through the void. It is a member of a small collection of galaxies known as the local group, and within this group, we are on a collision course. The nearest major galaxy to our own, the Great Andromeda Galaxy, is currently about 2.5 million light-years away, but that distance is shrinking. Pulled together by the relentless force of mutual gravity, the Milky Way and Andromeda are converging at a speed of about 110 kilometers per second. Visualizing this requires a profound leap of imagination. Two colossal islands of stars, each containing hundreds of billions of suns, each spanning over 100,000 light-years, are falling toward one another across the chasm of intergalactic space. In about 4.5 billion years, they will begin to merge. This will be a cataclysmic, yet strangely delicate, dance. The galaxies will pass through one another, their shapes distorted by tidal forces, while direct collisions between individual stars will be exceedingly rare. Due to the immense distances between them, the gravitational disruption will be monumental. Great streams of stars and gas will be thrown out into long tails, and the star formation rate will skyrocket as gas clouds are compressed. Over hundreds of millions of years, the two galaxies will coalesce into a single, larger elliptical galaxy, a process some astronomers have playfully dubbed the birth of Milky. This future cosmic smash-up is one of the most dramatic examples of motion on a grand scale, a gravitational destiny set in motion billions of years ago. Yet, even this galactic collision is just a local event, a detail in a much larger picture. For there is one final layer of motion, the most profound of all. It is the motion of space-time itself. In the 1920s, astronomer Edwin Hubble made a discovery that fundamentally reshaped our entire understanding of the cosmos. Using the powerful Hooker telescope at Mount Wilson Observatory, he observed that distant galaxies were not static in the sky. Almost all of them were moving away from us. And more startlingly, the farther away a galaxy was, the faster it appeared to be receding. This was the first observational evidence for the expansion of the universe. This is not motion times through time-space in the conventional sense, like galaxies flying away from a central point. It is the very fabric of space-time itself that is stretching, carrying the galaxies along with it. The most common analogy is that of raisins in a rising loaf of bread. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding. There is no center to this expansion. It is happening everywhere. This universal inflation is the enduring legacy of the Big Bang. Some 13.8 billion years ago, the entire observable universe was compressed into a point of unimaginable density and temperature. From that singular moment, it has been expanding and cooling ever since. The initial impetus of that primordial explosion set everything in motion, a cosmic shockwave that continues to propagate today. Every particle, every star, every galaxy carries within it the kinetic inheritance of that first cataclysmic instant. The reason nothing stands still is because the universe itself began in the most dynamic state imaginable, and its fundamental nature is one of expansion. The space between galaxies is not an empty void. It is an active, growing medium. This is the ultimate source of universal unrest. To be at rest in our universe is impossible, because the stage itself is in motion. This cosmic expansion is inextricably linked to the flow of time itself. The second law of thermodynamics, one of the most fundamental principles in physics, describes a property called entropy, which is essentially a measure of disorder or randomness. The law states that in an isolated system, entropy can only increase over time. A tidy, ordered room will naturally become messy. A hot cup of coffee will cool as its concentrated thermal energy dissipates into the surrounding cooler air. The universe as a whole behaves as such a system. It began in a state of incredibly low entropy, highly ordered and concentrated. And ever since the Big Bang, it has been on a one-way journey toward a state of maximum entropy, or heat death, where all energy is evenly distributed and no useful work can be done. This inexorable increase in disorder is what gives time its arrow. It is why we remember the past but not the future. The constant motion we observe everywhere, from colliding molecules to receding galaxies, is a physical manifestation of this process. It is the universe relentlessly exploring new, more disordered configurations. Motion is the mechanism of entropy's increase. A universe that was perfectly still would be a universe where time had no meaning, a universe frozen in a state of unchanging, maximum order, a possibility that the initial conditions of the Big Bang and the laws of physics seem to forbid. The constant flux we witness is the universe living, breathing, and aging. Albert Einstein, with his theory of general relativity, gave us an even deeper way to understand this relationship between matter, space, and motion. He revealed that space and time are not separate entities, but are woven together into a single, four-dimensional fabric, space-time. He also showed that this fabric is not passive or flat. It is warped and curved by the presence of mass and energy. Imagine a stretched rubber sheet. Placing a heavy bowling ball in the center will create a deep depression. A smaller marble rolled nearby will not travel in a straight line. It will follow the curve in the sheet created by the bowling ball. This is Einstein's vision of gravity. It is not a mysterious force acting at a distance, but a consequence of the geometry of space-time. Planets orbit the Sun not because they are being pulled by an invisible tether, but because they are following the straightest possible path through the curved space-time created by the Sun's immense mass. In this context, motion is the natural state of being. An object simply follows the contours, the geodesics, of space-time. To be still in a gravitational field would require a constant application of force, like a rocket firing its engines to hover above a planet. The ground beneath our feet is constantly pushing up on us, preventing us from following the natural, curved path toward the Earth's center. In a very real sense, the feeling of being stationary is the feeling of having our natural motion through space-time obstructed. The true state of rest, or free fall, is one of motion as experienced by an astronaut floating weightlessly in orbit. They are simply following the path of least resistance through the cosmic landscape, Einstein's masterpiece reveals that motion is not something that happens times within times, space-time. Motion is an intrinsic property of time space-time itself, the inevitable response of matter to the very shape of reality. So, we are left with a staggering and beautiful conclusion. The stillness we perceive is a localized, fleeting illusion, a trick of perspective. We are adrift in a universe defined by flux. We are composed of atoms whose electrons exist as clouds of ceaseless probability. These atoms form molecules that are locked in a violent, thermal dance. We stand on a planet that spins on its axis while hurtling around a star. This star, in turn, journeys around a galactic core at an incredible speed. Our galaxy itself is falling toward its neighbor, setting the stage for a cosmic merger of epic proportions. And all of this is happening within a universe whose very fabric is stretching, carrying everything along for the ride, a legacy of its explosive birth. From the quantum foam to the cosmic web, there is no escape from this dynamism. It is the core truth of our physical existence. This raises profound philosophical questions. If everything is in constant motion relative to everything else, what does it mean to have a location? What does it mean to be here? Our position is only ever meaningful in relation to another moving object. Our sense of place is a transient, relational concept in a cosmos, where there are no fixed coordinates, no absolute grid. We are all just patterns of energy, temporarily coherent structures, persisting for a brief cosmic moment as we are swept along in the universal current. This can feel disorienting, a loss of the anchor we call home, but it can also be liberating. It connects us to everything else in the universe. The motion in our blood is powered by the same thermodynamic laws that drive the expansion of the cosmos. The atoms in our bodies were forged in the hearts of stars that traveled for eons across our galaxy. We are not separate from the universe. Looking in, we are a part of its unfolding, a piece of its grand, kinetic story. The universal absence of stillness is not a flaw or a chaotic accident. It is the engine of creation, the source of change, complexity, and life itself. A static universe would be a dead universe, a place with no potential, no future. Our restless cosmos is a cosmos of possibility. It is a place where stars can form, where planets can coalesce, where life can emerge and contemplate the very motion from which it was born. The next time you hold a stone in your hand or gaze into a silent pool of water, remember the hidden universes of activity within. Remember that you are a passenger on a cosmic vessel, participating in a journey of unimaginable speed and scale. Embrace the flux, for in the unceasing motion of all things, we find the deep, vibrant, and undeniable pulse of reality itself. The universe never stands still because to do so would be to cease to be.